Hello and welcome to Friday's edition of Cracking the Cryptic. Now today on screen you can see an extraordinary looking puzzle by the constructor ProwlingTiger. Now we did a puzzle of his about a week or two ago, and I commented at the end of that this could be a new setter, a world-class setter in the offing, and the test results, our testers are saying this puzzle is absolutely world-class. So I think we're in for a treat today. This could be a difficult one though. You can see there's not a lot of information in this grid. It doesn't have the hallmarks of a classic Sudoku that you'd see in the newspaper. So I'm going to read you out the rules in just a moment. Quick reminder, if you haven't tried it yet, you must try the Sudoku Puzzle Hunt, which is available free on our Patreon site at the moment. Just click on the link under this video. That'll take you to Ben Needham's Sudoku Hunt, and it is absolutely brilliant, and there's a whole community of you guys over there discussing it. So there's a lot of help now actually available. If anyone is stuck on it and wants a pointer in the right direction, then you will find it over there on the Patreon site. And it's just brilliant from my perspective to see so many of you engaged in solving this work of puzzle art. Mark will be back later on as usual. During lockdown we're trying to keep our schedule of 2 videos a day, and so look out for, I'm not sure what puzzle he's doing. He might choose something from a recent championship, I think. So check that out later on. And with that, let me tell you about the rules of this puzzle. So normal Sudoku rules apply. In a normal killer Sudoku, the number in the top left-hand side of each cage denotes the sum of the numbers inside the cage, and numbers may not repeat within a cage. And additionally, in a normal little killer Sudoku, each arrow outside the grid denotes the sum of the digits along that diagonal, and digits may repeat along that diagonal. In this puzzle, no sums are given. Each sum is one of 2 numbers, both of which can be deduced. For example, the 2 sums could be 8 and 17, and therefore each cage or arrow sums to either 8 or 17. So you can see that this is a follow-up puzzle to ProwlingTiger's M&N puzzle, which I was quite pleased to come up with the sort of M&M soundbite there. But yeah, he did a puzzle recently that we solved where everything in the grid had to sum up to either M or N. Well, this works the same way, but in a far more extreme way. I mean, this is going to be extremely interesting, and not to say difficult. Do have a go at it. Click on the link under the video. That will take you to our webpage where you can play along. Looks like my mouse is working, so we're good to go. And with that, let's get cracking. Now, how do we do this? You can see I've when I put it in our software, I've left some room outside the grid, so that if we do manage to get some traction, we can actually put in what the cells can be. Actually, it's not working. One sec. Okay, that's better. Right. Well, the only thing I can see at the start that's in any way, well, that arrow, I guess. 1, 2, 3, 4, 5, 6. Okay, so if we think about this, what's the minimum sum that the yellow cells could have? If we put 1, 2, and 3 in each of these boxes, we'd have 6 in this box and another 6 here. So the minimum size of this arrow is 12. So we know one of the digits is at least 12. I'm not sure that is going to be enough to crack the whole puzzle. So the other thing I can see is that this box and this box both have cages within them that sum to M or N. And both, so both are completely contained in their 3x3 boxes. So we can, okay, let's look at this one. So I'm going to be thinking about the number 45, obviously, because we know that both of these 3x3 boxes will sum to 45 because it will contain all of the numbers from 1 to 9, and that's what you get if you sum those numbers. So here, the thing that attracts my attention is that we've got 4 boxes that sum to 45. Now, Therefore, it's not possible that there are two boxes of each of m and n, because if we had 2m plus 2n equals 45, you can see that that would imply that 45 should be even, which it's not. So this must be a combination of 3 of one digit, or 3 m's, say. Let's just call m. Let's say it's 3 m's and 1 n in this box. So if that's right, this box, what can we say about it? Well, okay, let me think about this. Well, we know that these 3 cages in this box are clearly not 3 lots of m, because 3 lots of m plus n is 45, according to this box. So this is not 3 lots of m, so is it 2 lots of m and 1 lot of n? No, it's not. Because again, if this is 3 lots of m and 1 lot of n, then 2 lots of m and 1 lot of n is equal to less than 45, axiomatically. So this box is either 3 lots of n itself, or it's 2 lots of n and 1 lot of m. Right, okay, so we're getting somewhere now, because if it's 3 lots of n, I can do that. 3, you know, if we've got 3n equals 45, n equals 15. And if n equals 15, then this box, which is equal to 3m plus 15 equals 45. So, right, so m here would be 10. So one option here is that m equals 10, n equals 15. Now the other one is a bit more tricky, isn't it? Let's just think about that. That one, we've got m plus 2n equals 45. So I've got m plus 2n equals 45 here, and I've got 3m plus n equals 45 here. Now I'm going to embarrass myself horribly by trying to do simultaneous equations in my head. Right. So sorry about this. This is going to be embarrassing. Right, I'm going to multiply this simultaneous equation by 2. So I'm going to get 6m plus 2n equals 90. And then I'm going to deduct this one. So 6m plus 2n equals 90. 5m equals 45. M equals 9. M equals 9. Does that work? So if m equals 9 down here, we've got 3 lots of 9 is 27, plus n equals 45. So n is equal to 18. Okay, that sounds plausible, doesn't it? So either, this is completely bananas. So either n is 18 and m is 9, or n is 15 and m is 10. Right. Now, what does that tell us? I have absolutely no idea. This box, is that what I'm meant to do next? You can see there's one cell sticking out of this box. So, okay, all right, well, we can work out the value of, or possible values of this cell, obviously, because we know that the whole box will add to 45, and we know we're going to have to add 4 different cages together to get a number that's greater than 45, and the amount by which it's greater than 45 will go into that cell. So let's carry on with our arithmetic. So you can immediately see, or I can immediately see, that 4 lots of the big number is nonsense. We can't have these 4 cages all being 15 or all being 18, because that square would then have to be enormous. So if we've got 3 lots, no, in fact 3 lots also doesn't work, does it? Because 3 lots of 18, for example, that's already 54. And then we've got to add in another load of stuff. That's all still going to make this far too big. So it's going to be, let's say it's the same with 3 15s plus a 10. So we're going to be looking here at, so we're going to be looking at 2 of each. So 2 18s plus 2 9s is essentially equal to 3 18s, which is 54. So if all of these cells add to 54 and these add up to 45, that cell would be a 9. If, on the other hand, we've got 2 lots of 15 is 30, plus 2 lots of 10 is 20, that's 50, that would be a 5. So I've got this down to being a 5 or a 9. Okay, that's still no use at all. There's nothing else to do. This must be the trick. Ah, yes, it is the trick. Look, if that's a 9, we can't put a 9 in this box. No, we can't put a 9 in the box. Oh, that's it. Look, because now we're in the iteration where n equals 18 and m equals 9. So we know each of these cages sums to either 18 or 9. So where on earth can I put a 9? I can't put a 9 here because it's in the same cage as this 9 anyway. So I've got 3 possible slots for the 9. But if I put a 9 in here, then the only way of getting to 18 now is if I put another 9 in there. Similarly in this box, if one of them's a 9, the other one has to be another 9. This cannot be a 9. That's a 5. We've got a digit in the grid. 5. Oh, this is so clever. This is so clever. So now we actually know m and n. We know n is 15 and m is 10. So we have there's an enormous constraint. There's 5 places on this box. Where can we put the 5 in it? Well, it can't go in the same cage as this 5. If the 5 goes in a domino, the other cell in the domino would either have to be another 5, because m is 10, or it's got to be a 10 because n is 15. Both of those are invalid, and there's only dominoes. Apart from this triple here, then this 5 rules out those 2. That is a 5. Now you can't put a 5 in a domino. That is something we've established. So the 5s are in one of those 2 cells. Up. This can't have a 5 in it. This can't have a 5 in it because it's a domino. The 5s must be down there. 5's in one of these 3 squares. Now this box up here has 15s in it, doesn't it? 3 lots of n was where we got to with this. So I don't think we can tell which way round that goes. No. There's no 5s in dominoes. No 5s in dominoes down here. So the 5 must be over there. That's right, that must be right. So the 5 is locked into one of these 3 squares. This is not 5. We get another digit in the grid. 5 is not in a domino again. 5 goes here. It doesn't go there. What an incredible puzzle. Nothing in the grid to start with apart from a 1 9 and this bizarre constraint. And the logic is just gorgeous. Now, come on. What next? The truth is, I'm not at all sure. Okay, come on. Let's try and spot something here. So 2 of these cells add up to 10. Oh, hang on, this 5 now on this diagonal. That is incredibly important because this arrow now, we know it adds to 10 or 15. Well, it can't add to 10 if there's a 5 there. It could never have added to 10 actually because it had to be 12 or higher. So this now adds up to 15. We can put that in using a central notation. And that means these 5 cells have got to add up to 10. Now, that is quite restricted, isn't it, all of a sudden? So this could be 1, 2 and 3, which would make these two 1 and 3, or this is 1, 2 and 4, and this would be 1 and 2. So there's always a 1 in one of those squares, and there's always a 1 and a 2 in those squares. And the other digit is either a 4 or a 3. So we've got this 1 degree of freedom going on. I really would like to get rid of that. Now, I'm wondering about the 9, because yeah, 9 can't go in those squares because of this 9 here. Now, 9 can't go in this cage with a 5 either now, because if it does, 9 plus 5 is 14. We'd need the other digit to be a 1, and it can't be a 1 because 1 is on this diagonal. We know that this diagonal cannot have a 9 on it, so the 9 is definitely in one of those squares. Can we get rid of it from here? So this is 15. So if this is a 9, these two squares have to add up to 6. So the only way, we've got 5 there. So they couldn't be 1 and 9. They'd have to be 2 and 4. Now, is that ruled out by anything? Answer is I'm not sure it is, because if we had, it would have to be like this. It would have to be 2, 4 like this. Oh, it is ruled out. Of course it's ruled out. I'm being slow here. Sorry, guys. No, the reason it's ruled out is that if this is 2 and 4, this has to be 1 and 3, and you can't get to 15 in this cage. So the 9 cannot go there. The 9 must go here. And these two skulls have got to sum up to 6 now. So they can't, yeah, we can't have 1, 2 and 3 down this diagonal. It's impossible. It's not big enough. This has to be 2 and 4. And this has to be the 1. Sorry, I was a bit slow there, but I'm getting there. Now these two squares, now there are no degrees of freedom now, because this has taken up one of the one that we had. So this has to be 1 and 2. This square, because this is a 1 or a 2, we never get to 15 in this domino. So this is an 8 or a 9. So this one is done. This one is not done yet. Oh, now hang on. This 9 must be in one of those 3 squares. Well, if the 9 is in this one, it has to be accompanied by a 1 to make 15. So 9 can't be there. 9 is there, which means this has to be a 1 or a 6, doesn't it? Now, can we deduce that that is one of those options is not allowed? I'm trying to remember what we concluded. We said this box here had 2 M's and 2 N's in it. I've just seen, look, that 9 gives me an 8 there. Let's put that in. That's an easier win. Ah, that is an easier win because this 1 now is helpful. Where does a 1 go in this box? It can't go here. If it goes here, it has to be accompanied by a 9, and it can't be because the 9's already in the box. So the 1 does go there. There's a 1 down here. This is mind-bending, this puzzle. This is one of those puzzles I'm going to have to go and put a cold towel on after I've finished it, assuming I can finish it. Come on. So 2. I'm not sure how to do that bit. 9s, 1s. There's nothing going on down here on this right hand side. There's this arrow here. This 2 is quite important because if we look at this box, if the 2 is on this side, what do we have to put into its equivalent domino shape here? So if this was a 2, what does this cell have to be? Well, because we can't make this equal 15 now because 2 is too small, it would have to be an 8, and it can't be an 8. So the 2 is not down the left hand side of box 9. It must be in one of those cells. And now there must be a 2 in one of these 3 cells. So this has either got a 3 in it or it's got an 8 in it. We've got 3 digits there as well. This box, this is going to be where we need to look. We've got a 3-digit sum here, which has to be 10 or 15. We've got 1s. Yes, I've got it, I think. This one pushes a 1 into one of these dominoes. Now that means that one of these dominoes, it can't be this one actually because of the 9 here, but one of these dominoes must contain a 1 and therefore must contain a 9 in it. So either this is a 1-9 pair or this is a 1-9 pair. Now if that's true, let's come back up here and ask whether a 1 can ever go in a domino. It can't, because if I put a 1 in here, I can't put a 1-9 in either of those dominoes down there. Ditto. The only other cell that could be a 1 is this one, and if that's a 1, that also is going to force a 9 here, and that's also going to break my dominoes down here. So actually in this box, I think that square has to be a 1. And that means one of those 2 squares is a 1 and one of those 2 squares is a 9. And there must... no, there could be a 1 in this domino. I think the 1s are over there somewhere. I think that's all we can say. But now this sum is interesting all of a sudden, because now this is a 3-cell sum that doesn't include a 1, and that if this was a 10 sum, therefore there's only one way to make 10 in 3 cells without using a 1, and that's 2, 3 and 5, and look, there's a 5 here. So this is a 17 sum. This is a 15 sum. That is a 15 sum. Right, it's a 15 sum. How do I do it? So the 9 in this box, is that restricted? 9. I feel like it is, and I'm not appreciating something about it. If the 9 is here, these squares would have to be 2 and 4. That looks possible with a 2 there and a 4 there. Oh, no, I know what I can do. I've forgotten. This box has got 3 lots of 15 in it. So if this is a 1, this has to add up to 14 without using 9. That's a 6 and an 8. These must be 3, 5 and 7 to finish the box here. So now this can't be a 2. If that's a 2, that has to be an 8, and it can't be an 8. So the 2 shifts up to the top. That's an 8 now. Look, that pushes an 8 down here. So this triumvirate down at the bottom is a 2, 5, 8 triple, which obviously adds up to 15. So these are all, we've got 3m plus n in this box, so these all add to 10. So we've got the 1, 9 sort of penciled in. There's also got to be a 3, 7 and a 4, 6 down here, which means this can't be a 3, 7 pair. And if it can't be 3 and 7, the 3, 7 must be here. In fact, this can't be anything. This can't add up to 10. Because if this adds up to 10, you can see it can't use 2 and 8. It can't use 1 and 9. So it would have to be 3, 7 or 4, 6, both of which break these totals down here. So this has to add to 15, and it can't use an 8. So this is 9 and 6. Good grief. Now, 9, 6. That forces the 6 over there, which forces a 4 over here. This must have a 4 on this side. So let's put 3, 4, 7 in there. These two squares now must be, what's that, 6 and 9? 9 here, so that's a 9. That's a 6. These squares have got to be 3, 4, 7. And now the 15 total disambiguates some of this. That's going to put a 7 in there to make sure this adds to 15. No 7 up there. Wow. Wow, wow. What a puzzle this is. 28 minutes. I think I'm doing quite well in 28 minutes. This is not easy. Right. What on earth do I look for now? The 7 shifts a 7 into that cell. That's the only place a 7 can go. That gives me a 3 and a 5. Now 5s, look, must be in one of those two positions. And this one can't be a 1 anymore because that would place a 9 here, and there's a 9 there. So we've got a 1, 5 pair. Just doing some normal Sudoku. 6 must be in one of those 3 squares. 8 must be in one of those 3 squares. Nine must be at the top. 7 must be at the top. Sorry about this. I feel like I'm being a bit pedestrian. I'm not quite sure. So this square has to be a 2, 3 or a 4, just looking at the... now, okay, so we can do some stuff with this. because 2, 3 and 4 make this domino adding, it can't add up to 15 if this can only be a 2, 3 or a 4. So we know it adds to 10, therefore this can't be a 3 because the 7 here gives us a problem with that. So this has to be 6 or 8. Nines here and here, shift a 9 into one of those squares, look. Ones. We've got the same trick going on, look, with dominoes and ones. We can't put a 1 in here because that would have to be a 9. So the ones must slide over into just one of these two places. Now look, ones are locked into column 1 and column 2 in two different 3x3 boxes. So where does the 1 go in? Yeah, this is okay. Yeah, where does the 1 go in column 3? It's got to be in one of these 3 cells, and it can't be here, because a 1 here would put a 9 here, and it can't be a 9 there. So 1 is in one of these 2 cells. Now look at that. All of those digits are odd. So these are definitely even. Right. Okay, now there is something interesting here, look. I don't think it's necessarily going to be that helpful, but those 3, if we look at this diagonal here, we know this sums to 10 or 15. But we know those 3 cells together absolutely have to be an odd number, because we're adding an odd number to 2 even numbers. So, but if we look here, we're also adding an odd number to an even number in this cage. So these, what this means is that whatever this sums to, whether it's 15 or 10, these also sum to that same total, because the parity of these cells is the same. Therefore, once we add the parity of this cell to the same, we are retaining the parity for this cage and for this sum. Now, I'm not actually sure that's very helpful. So it's either 2 lots of 15 or it's 2 lots of 10. This digit here has got to be 2, 3, 4, or 7. Well, okay, we can immediately eliminate 7 from here, because if this is a 7, we can see from here it's impossible to make these 2 squares add up to 8. So we're looking at a total of 10 for this, this triumvirate. Therefore, these have to add up to 10. With a 7 here, that's just impossible. It doesn't matter what we put into those 2 squares, we break the bank. So this has got to be a 2, 3 or a 4. Now, I'm not quite sure what the best way is of disambiguating this. Let's see if we can see a good way of doing it. So, well, let's ask if this can be an 8. Because if this is an 8, we automatically know we're looking at 2 15 sums for certain. So, and in fact, if this is an 8, because that's a 6 and that's a 4, we get 8, 4, 1 into those positions. Now 8, 4 and 1 add to 13. This would have to be a 2, and these 2 squares would have to add up to 13, but they can't, because to do that we'd have to use 5 and 8, and that repeats the 8 in both of those squares. So we've managed to get that down again. That is not 8. I wonder if I can get rid of 6 here, we're happy days, aren't we? So let's try 6. If this is 6, 7, Yeah, if this is 6, we're into 15 land again, aren't we? Because I can't make these two squares add up to 3. So if this is 6, I need these two to add up to 8. They'd have to both be 4. Which repeats the 6 this time. So let me just show you what I'm doing there. So if this is a 6, I need those to both be 4 in order to get up to 15 in this direction. We know from parity this must equal 15 as well. That means these add up to 11. Well, we can immediately discard the 1. The 5 would be the only option, and that would have to be accompanied by a 6, which breaks. So why do I think that's important? Well, because if that's not a 6, now I've got a 2-4 pair here. So this can't, oh, I don't know what happened there, but I don't want that to be a 2 or a 4 now. So now I've got this down to being a 6 and an 8. And most importantly, in this diagonal, you can see I can never get to 15. So now I'm looking at 10 sum. I can immediately write in a 6 here, because if I put an 8, I can't make both of those a 1. So this is a 6, I think. This is an 8. That becomes a 2. That's a 4. 7, that must be the 3. That must be a 1. That must be a 5. Up here, we can do some, we need... What do we need? We need 3, 7 and 9. Oh, that's going to be good. Because, look, that disambiguates that one. 4, 3, 2, 4. That can't be 3. This, now that one, look, it sees an 8 and it sees 2 9s, so it can't be 15. This is a 10 sum. I need to notate that somehow. I'll make 10 sums purple. That's purple. So I've done this one, I've done this one, I've done this one, I've not done this one, I've not done this one, I've not done this one. There might be a restriction there. Obviously, if that sums to 10, it can't use a 1. It would have to be 2, 3, 5. That would place the 5, 5, 2, 3. That would have to look. 5, 2, 3. That's an 8. Could be a 7. That might. I'm not sure. I might come back to that. That is. I can see it's constrained. This column is interesting as well, look, because I've already got 22 in it. So these cells add to 23. But these cells here, I can narrow the value of. So I'm going to be able to deduce the value of this cell, at least within a few options, I think. So 22. These add to 23, which is an odd number. So, what can we say about that? If this is 5, this could be, well, unfortunately, this could be 10. That would make that an 8. If this is 5 and this is 15, that would make that a 3. If this is 10, on the other hand, and this is, now that then can't be 15, that would break the bank. Is it always 3 or 8 here? That's what that seems to suggest. This is either 5 and 15 or 5 and 10. That gives the 3 or the 8. If it's 10 here, this now can't be 15. It just can't be. So this is always 3 or 8. I should have looked at this before. That's a massive restriction. So this square here, if it's 8, that could be 7. If it's 3, that could be 7. And if it's 8, I suppose that could be 2. That can't be 2. Oh, lordy. I think that 2 came from this logic. So I still would have been left with a choice here if I'd looked at this before. So I don't think it's that bad. But yeah, this I think has to be a 7. Therefore this, that still doesn't disambiguate that square. That's ironic. But this is massive now, because this sum, let's make that, this will be the 15 colour, the light blue. So that has to add to 15 because it can't add to 10 because the 1's not in the sum. So these two have to add up to 8. That means that square, look at that. That's beautiful. So this can't be a 7. So we know these two add up to 8 to make 15. If this cage adds up to 15, this 7 would be repeated in the box. So this adds up to 10 and this is a 2. That places a 2 in one of those two squares. And this, look at this. Now this one, that must be a 10 sum because we can't get to 15 anymore, so that's an 8. And these two have to add up to 8 without using 1 or 2. So this has to be 3 and 5. That's a 3 at the top now. We said that added up to 10, didn't we? It can still be either. It can still... Oh no, it can't because of the 1 here. So if this adds up to 10, this has to be 4, 6. I think logic seems sound to me, so let's go with it. That's a 6, that's a 4. Where does 2 go in this row? It must go here. That square there should be a 7 to complete the row. That 7, look, could accompany an 8 or a 3. Bother. This 8 sees that one. That's a 3 now. Oh, right. So that's important for this cell, look. Because this cage, we didn't know whether it added up to 10 or 15. Well, it can't add up to 10 now because I can't make these two squares add up to 5 because the 1, 4 and the 3, 2 are ruled out. So this definitely adds up to 10. Oh, it can be 2, 8 or 4, 6 though. We've got 2 and 6 there. Right, so this is a 2 or a 6. This is a 4 or an 8. It's still possible. I don't believe it. I don't believe it. Okay. Down here, look, we still need to place a 9 in this column, so it must go there. That's a 1. That's not a 1 now. And that's not a 5 either. So this has become a 1, 5 pair. These two squares have got to be 4 and 6. There's a 4 here, so that's a 4, that's a 6. This can't be a 4 now, because although that would equal 10, the 4 would clash, so that must be a 9 to give us 15. That's not 9. The 9, 7 is disambiguated at the top. This is some puzzle. Some puzzle, this. 7 and 8 here. This 4 tells us that the 4 must move up there, which gives us the 6, the 1 and the 9. This square is not 4 now. So I've now used up almost all of these clues. I haven't used this one yet. And in fact, if we look here, this block, I need 3 and 7, don't I? So this is a 3, 7 pair. Now surely that's going to allow me to disambiguate this. If this is 6 and 1, oh, actually look, I've got 1 here. So that's 1, that's 5. So this has to add to 15, that has to be a 3. that can't be 5, that can't be 2, and that one can't be 8. That one can't be 5 either, so that's 2, that's 8, that's 5. This square is a 6. That disambiguates the 6, 8 at the top. This square must add up to 10, because it can't add to 15, because the 9 and the 7 have both gone. It can't be 1, 9, 3, 7, or 4, 6, so it's 2, 8, 2, 8, 4, 6, 4, 3, 8, 8, 7, 2, 3. Now I don't want to mess this up now. You can see I need 4 and 7. I think that looks good. That looks good. The checking function won't work because this is a very unorthodox grid, but that would be what I would submit. Wow, what a puzzle. Eminem's difficult second album there, dealt with. ProwlingTiger, you've outdone yourself. I loved it again. It was very, very hard, with some interesting maths at the start. So I hope you guys enjoyed watching me struggle through it, and we'll be back later with another edition of Cracking the Cryptic.